A laser weapon does not simply fire at a target. It does not behave like a bullet, or a missile, or any object with mass. Instead, it must do something far more difficult. It must place energy, precisely and continuously, onto a point in space that is moving, vibrating, and often trying very hard to escape. And it must do this not once, but for seconds at a time. This is why the true challenge of laser weapons is not power. It is tracking. Because firing a laser is easy. Keeping it on target is not. To understand why, we need to step away from the idea of lasers as futuristic weapons, and look at them for what they really are. Extremely demanding control systems, operating at the limits of physics, perception, and prediction. The story of laser tracking is not about light itself. It is about motion, uncertainty, and how engineers attempt to control both. Light travels at extraordinary speed. So fast that, on human time scales, it appears instantaneous. This creates a common assumption. If light is that fast, aiming it should be trivial. But speed is not the same as control. A bullet carries momentum. A missile carries guidance hardware. Once launched, they have physical presence in the world. A laser does not. The moment light leaves the weapon, it is already gone. There is no steering it mid-flight. No correcting its path after emission. Every correction must happen before the beam is fired. And that makes tracking the central problem. Imagine trying to hold a magnifying glass in sunlight, keeping the bright focal point on a moving ant. Now imagine the ant is flying at hundreds of kilometers per hour. The air between you and the ant is shimmering with heat. And your own hands are shaking from vibration. That is a simplified version of what laser weapons face. The target is rarely still. The platform carrying the laser is almost never still. And the environment between them is constantly changing. Tracking means solving all of these problems at the same time. At its core, laser tracking exists because light behaves differently from physical projectiles. A projectile can miss and still cause damage nearby. A laser cannot. For a laser to be effective, energy must remain concentrated on a small area of the target long enough to heat, weaken, or disable it. That requires stability. But stability is exactly what real-world conditions refuse to provide. Targets move. Platforms vibrate. Air bends light. Each of these introduces error. Individually, those errors may seem small. Together, they become overwhelming. And unlike a missile, a laser cannot compensate after launch. This is why laser weapons do not aim in the traditional sense. They predict. The process begins long before the laser fires. First, the system must detect a target. This is not done with the laser beam itself. Using the weapon beam for tracking would be inefficient and unreliable. Instead, laser systems rely on a network of sensors. Infrared cameras detect heat signatures. Optical sensors track visible shape and contrast. Radar systems measure distance and velocity. Each sensor provides incomplete information. But together, they form a picture. This picture is never perfect. It is noisy, delayed, and uncertain. And yet, decisions must be made from it. Once a target is detected, the system does not ask, "Where is it?" That question is already outdated. Instead, it asks, "Where will it be?" This is the heart of laser tracking. Because by the time a laser fires, the target has already moved. So tracking systems rely on prediction. Computers analyze position, speed, direction, and acceleration. They look for patterns. They estimate intent. Is the target accelerating? Is it maneuvering randomly, or following a path? Based on this, the system predicts a future position often just milliseconds ahead. That prediction is updated continuously. Hundreds. Thousands. Sometimes tens of thousands of times per second. Tracking is not a single calculation. It is an ongoing negotiation with reality. But prediction alone is not enough. The laser must physically point in the correct direction. And this is where another misconception appears. Most people imagine a laser weapon turning like a turret. Slow, mechanical, visible. In reality, large movements are avoided whenever possible. Instead of rotating the entire system, laser weapons rely on internal beam steering. At the heart of this is a set of extremely precise mirrors. These mirrors are small. Very small. They are mounted on actuators capable of microscopic movement at incredible speed. By tilting these mirrors by tiny angles, the system can redirect the laser beam almost instantly. This allows rapid correction without moving heavy hardware. The mirrors respond not in seconds, but in microseconds. This speed is essential, because even the smallest delay can cause the beam to drift off target. However, even perfect aiming is not enough. Between the weapon and the target lies the atmosphere. And the atmosphere is not empty. Air is a dynamic, chaotic medium. Temperature differences create density changes. Density changes bend light. This phenomenon is called atmospheric turbulence. It is the reason stars appear to twinkle. It is the reason distant objects shimmer on hot days. For a laser weapon, turbulence is a constant enemy. As the beam travels through air, it spreads, bends, and distorts. Left uncorrected, this distortion can reduce effectiveness dramatically. So the system must compensate. Laser weapons do not fight the atmosphere by brute force. They fight it by anticipation. Tracking systems measure how the atmosphere is affecting the beam. They do this using reference beams, sensors, or feedback from the target itself. From this data, the system calculates how the air is distorting light at that moment. Then, something counterintuitive happens. The laser beam is intentionally distorted before it is fired. Its shape and phase are adjusted so that atmospheric effects cancel out during flight. By the time the beam reaches the target, it has corrected itself. This process is known as adaptive optics. It is one of the most sophisticated techniques in modern engineering. And it must operate continuously, because the atmosphere never stops changing. Now consider what happens when all of these systems operate together. Sensors detect motion. Computers predict future position. Mirrors steer the beam. Adaptive optics correct distortion. All of this happens in real time. All of it must stay synchronized. If any part lags behind, the beam slips. And slipping, even slightly, can mean failure. This is why laser weapons are often described as control systems first, weapons second. Power matters. But control matters more. This leads to one of the most common misunderstandings about laser weapons. Movies often show lasers locking onto targets instantly. A beam appears. The target is destroyed. Reality is slower. Laser weapons usually require sustained contact. Energy must accumulate. If tracking is lost for even a fraction of a second, the process resets. This means effectiveness depends on stability over time, not instantaneous accuracy. A powerful laser with poor tracking is ineffective. A less powerful laser with excellent tracking can succeed. This inversion surprises many people. But it reflects the true challenge of directed energy systems. Another misconception is that lasers are immune to countermeasures. In reality, anything that disrupts tracking reduces effectiveness. Rapid maneuvers. Reflective surfaces. Smoke or dust. None of these stop light entirely. But they increase uncertainty. And uncertainty is the enemy of prediction. Laser tracking systems are constantly balancing confidence and correction. They are never fully certain. They simply become confident enough. Why does this matter? Because tracking determines what laser weapons can realistically do. It defines engagement range. It defines target types. It defines reliability. Against slow, predictable targets, tracking is easier. Against fast, agile, or erratic targets, it becomes harder. This is why modern laser systems are often designed for specific roles. Drone defense, rocket interception, close-range protection. Each role imposes different tracking requirements. And improving tracking expands those roles. Looking forward, advances in laser weapons are likely to focus less on raw power and more on intelligence. Better sensors, faster processors, smarter prediction algorithms. Machine learning is already being explored to recognize movement patterns. Instead of reacting, systems may anticipate behavior. This does not remove uncertainty, but it reduces surprise. And in tracking, reducing surprise is everything. In the end, laser weapons are not about shooting light. They are about understanding motion under uncertainty. They are about measuring the world, predicting its future, and acting faster than change itself. The beam you see is the final expression of thousands of calculations, corrections, and compromises. The real weapon is not the laser. It is the system that keeps it on target.